Hi, good morning. I am Chris Argamino, the equipment specialist of the DLSU Spectroscopy Laboratory, and I'll be your first speaker for this morning's event. So my discussion will be on the atomic and molecular spectroscopy for sustainability research. Overview muna. Section 1 would be the definition of sustainable development and an overview of the UN SDGs. And then we'll be moving on to the basics of spectroscopy. Section 2 would be a focus on atomic and molecular spectroscopy. And then section 3, lastly, would be the applications of these techniques to achieve the UN SDGs. So first, let's have a brief background lang on sustainable development. So in 1987, if you're not aware before, now you are now. So in 1987, the World Commission on Environment and Development published the document A Common Future, where the famous sustainable development definition was coined. Wherein the needs of the present are met without sacrificing the capacity of the next generations to meet their own needs. So later on, the pillars of sustainability were also established, and these includes economy, society, and the environment. So fast forward to a few decades later, the Sustainable Development Goals were developed or introduced. So the SDGs, also known as the Global Goals, were adopted by the UN in 2015 as a universal call to action to end poverty, protect the planet, and ensure that by 2030, that is 9 years from now, all people enjoy peace and prosperity. So the 17 SDGs, these are integrated, and they recognize that action in one area will affect outcomes in others, and that development must balance social, economic, and environmental sustainability. So the pillars I mentioned earlier. So throughout this session or throughout this mini symposium, you'll be seeing these SDGs in the discussion of each speaker this morning. So we now move on to the basics of spectroscopy. So definition muna, spectroscopy is defined as the study of the interaction of matter and radiated energy. So we have two questions here. The first one would be, ano ba ang radiated energy? What is radiation? Ano bang tinutukoy natin dito? So yun yung unang tanong. And pangalawa, anong mangyayari sa matter natin, sa atom, sa molecule, if these are exposed to certain types of radiation? So those are the questions that you will be answering in the next slides. So here we have an electromagnetic spectrum wherein you can see the relationship na kapag mas mataas yung wavelength, for example, in the case of radio waves, mas mababa din yung energy. So suffice to say that in this particular scenario, I'll be focusing kasi on infrared, visible, UV, and X-rays. So mas mataas yung wavelength ng infrared, and among these four, it has the lowest energy, whereas yung X-rays natin, it may have the shortest wavelength among the four, but it has the highest energy. And those will come into play later when we talk about the interactions of these types of radiation with matter. So we have here a diagram showing some electronic transitions or energy transitions. So the typical transitions that we may be familiar with is the absorption phenomena, wherein once an atom absorbs a specific wavelength, then an electron from the ground state may jump to the excited state, and the energy released will be utilized to by a specific instrument to for a particular analysis, which may be qualitative or quantitative. Now, absorption may happen if the atom or the material requires incident light or external radiation. Now, sometimes spontaneous spontaneous emissions happen wherein the material itself, the atom itself, matter itself will be emitting light. And in that case, the emitted energy or emitted light will be detected by the instrument. Sometimes stimulated emission happens, or you can call it fluorescence actually. So in fluorescence, matter will be absorbing a certain wavelength, and then that wavelength, after absorbing a few milliseconds or nanoseconds later, it will also be emitting energy at a typically or usually higher wavelength. So if that happens, then we can say that fluorescence has occurred. So this types of phenomena will happen if you expose your matter with relatively high energy like X-rays, UV radiation, or visible radiation. Now, in contrast to those three, infrared radiation is quite weak in terms of energy. So instead of making these electrons jump, what can it can only induce for a molecule are certain vibrational relaxation transition. So for example, you can see here in the illustration in the presentation that these stretches, bendings, rocking, scissoring may happen to your molecule, and that can be read. And the energy released through these transitions can be analyzed or read by the instrument. So what are the basic components of these equipment that I've been mentioning earlier? So disclaimer lang, this is just a sample signal flow and does not apply to all cases. So for example na lang, radiation source may not be needed if emission yung system. Okay, so again, these are the instruments or parts of the instruments. So radiation source, we have the wavelength selector, which could be a monochromator or a polychromator, depends on the need. Sometimes it could be an interferometer as well in the case of FTIR. Sampling device could be a cuvette for UVs. It's a transparent glass or transparent quartz system, container. It could also be a flame atomizer or a graphite furnace atomizer for AAS. It could be a film holder, or it could be a reflectance attachment for FTIR. It could be a lot of things for different instruments. The bottom line here is that it contains your sample, or it's your sampling device. And then once the light from the wavelength selector and sampling device passes through, it will be reaching a detector where light energy is converted into electrical energy, and that electrical signal is converted into an output which we can interpret. For example, it's usually in intensity case units or absorbance units. Whatever the case may be, we will be seeing it on a screen, on a PC, or on a monitor or an output device. So next item would be the discussion on specific types of spectroscopic techniques. In this case, we have atomic spectroscopy. So now, how do we convert our samples, or how do we ensure that only atoms are analyzed? So we have two different types of systems here. We have AAS and ICPOS, which converts your aqueous solutions or aqueous samples, aqueous analytes into gaseous atoms. So the high heat, so it's around 2,000 to 3,000 Kelvin for AAS, and it's 5,000 to 10,000 Kelvin for ICP. This high temperature ensures the conversion of your aqueous solutions into gaseous atoms, aqueous samples into gaseous atoms. Now it's another case. It's a different case for X-ray systems, because instead of utilizing high temperature to ensure the conversion of atoms, instead of high temperature, we utilize high energy naman of the X-ray. So what happens here is that instead of the typical transition by the UV invisible light kasi yung ginagamit sa AAS and ICPOS, for X-ray naman, it's X-ray. So since mas mataas yung energy, instead na yung mga outer shell electrons yung tinitira niya, it's actually the inner electrons. And once these inner electrons are hit, so magkakaroon kayo ng empty na shell sa loob. Siyempre hindi pwede yun kasi kailangan maging stable ng atom. So mangyayari, the outer electrons from the outer shell will move to the inner electron, and then the energy released will be detected by the instrument. So yun yung ginagamit natin dito sa XRF. So trivia lang, yung mga nagfi-feel, for example, FDA, for example, a few years ago, I remember this news na nagkaroon nga ng nagkaroon ng parang threat ng lead contamination sa mga toys sa Divisoria ba yun o Baclaran. And then what they actually used there, I remember, is a handheld XRF to monitor the contamination in the surface of the toys. So yun nga lang yung difference dito. It's more of surface analysis as compared to the AS or ICP na kailangan mong i-digest or yung bulk ng sample yung ma-analyze mo. So those are the two cases dito sa ating atomic spectroscopy. So difference, again, yung pinaka-obvious would be emission yung ICP, absorption yung AAS. Emission kasi hindi mo kailangan ng incident light, or unlike sa AAS that you will be needing a hollow cathode lamp to for your analysis. So we have a flame here, or graphite furnace here, compared to your plasma sa ICP. Tapos we both have wavelength selectors. The difference is that for AAS, in most cases, it's a monochromator, allowing only one wavelength to pass through at a time, and allowing one element to be analyzed at a time para makarating dun sa detector, which is a photomultiplier. So now, the difference for the ICP in most cases is that it utilizes a polychromator, wherein it allows multiple or simultaneous wavelengths to pass through and enter a detector, appropriate detector. In this case, it's a CCD, or charge coupled device. So this allows faster analysis kasi simultaneous yung analysis. For example, if you were used to analyzing, let's say, individual elements for AAS, sa ICP kahit sabay-sabayan okay lang. So that's the main advantage, kaya rin siya mas mahal actually. Alright, so moving on, we have this table comparing detection limits. So flame AAS, siya yung pinaka least sensitive. So it's a 1 to 100 ppm lang. So lang yun kasi compared to the ICP-MS in this case, kaya kasi ng 1 ppb to 1 ppm to in some cases 2.001 ppb. 1 ppb pala yan. So yun yung difference nila. And then again, if you're going to purchase, if you're going to require atomic spectroscopy techniques, then you must know these detection limit differences. Now, if you will be requiring very trace level analysis, then contact us kasi meron kaming ICP-MS dito sa CIF, and just send us an email at cif@dlsu.edu.ph for more details. Next would be molecular spectroscopy. So as you can see here on the screen, may mga nasa logo. It means that meron po tayo ng mga makinang to dito sa CIF. So just, again, send us an email if you need these services. So for the UVVIS, what we actually have here is not only the typical cuvette system, but we have a reflectance system available. So if you need analysis on the reflectance of UV invisible light for your solid samples, then we can do these analysis for you. So FTIR naman, what we have is an ATR system. So you may be familiar with the transmission system kung saan may gumagawa kayo ng pellet or nag-analyze kayo ng films. But here we have a much simpler system wherein we have a diamond crystal here, and then just place your sample there, whether solid or liquid. For solids, you just ipit the sample. Ipitin mo lang yung sample and then read mo na. So ganun kabilis. So for those in the pharma industry, you may be much familiar with this kasi most of you already utilize this technology para mas mabilis yung analysis. And then we also have an elemental analyzer which actually uses chromatography systems in most cases, but it actually has an option for the use of an infrared detector for the analysis of oxygen and sulfur in particular. So yun kaya siya nandito. And then lastly, we have dynamic light scattering spectrometers. So this uses an APD detector. And this can be used if you want to know the particle size, hydrodynamic particle size of your samples, as well as the zeta potential and other applications pa. So what we have in the CIF is a nano level dynamic light scattering spectrometer. So if you'll be seeing later some applications of this one. So next, we have another set of signal flows. So ang difference ng radiation source dito from the AAS sa UVVIS is that instead of having hollow cathode lamps na specific for each element, we have two types or two sets of lamps typically. Sometimes isa lang kung kaya. So xenon arc, kaya niya na yung from deuterium or from UV to visible region, while if you for most cases, it's deuterium lamp for the UV light and tungsten lamp for the visible light. So regardless of the radiation, it will pass through a monochromator. And then yung sample compartment could be a cuvette, could be the reflectance system that I mentioned earlier. And then lastly, i-receive siya ng detector. It could be a photomultiplier tube. So it's a common theme for spectrophotometers, yung PMT. Sensitive kasi siya. It could also be other detectors like InGaAs or lead sulfide for those which will be going pa towards the NIR detection. So we have the FTIR. This is mistaken. It should instead of xenon arc lamp, we have a heat source. So hindi siya yung visible light or UV light na typical. It's actually heat or IR radiation which is emitted by this radiation source na dadaan sa interferometer, which is the wavelength selector for the FTIR. And then after the interferometer, we will be going to the sample compartment now, which could be a lot of different things. Could be film holder, KBR pellet, ATR, or diffusive reflectance. Maraming options for the ATR depending on your need. And then we have the detector lastly, wherein in most cases nowadays, pyroelectric detector yung ginagamit for the typical FTIR system. So now we move on to the applications of these technologies to achieve the UN SDGs. So unahin muna natin yung clean water and sanitation, SDG 6. So here, it's a quite common, sabihin natin quite common siya na technique or na analysis, yung drinking water analysis kasi it's actually required by the government for drinking water to be tested according to the Philippine National Drinking Water Standards ng DOH. So here, they used ICP-OAS for the ppm level elements kasi dun sa drinking water standards ay may limits. So may mga ppm, ppb. So ppb naman, they use graphite furnace AAS. So again, this can be replaced by an ICP-MS if you need them. So it's a quite relatively easy and available study kung may AAS ka to perform. Kasi siyempre very important yung drinking water sa atin. Sino bang di nangangailangan, di ba? So it's actually an indispensable study to perform in your own locations or settings. So next would be a research na ma-achieve yung zero hunger and good health and well-being. So this study is entitled Determination of Heavy Metal Content of Processed Food Products from Terran's Market using ICP-OAS. So again, you can use these instruments actually to perform a risk assessment study. So advantage, ang daming elements, di ba? Kung AAS gagamitin natin, mas matagal, pero pag ICP, simultaneous to kaya in most cases. Ayan. So next would be ulit siya, life on land. Yan. So life on land, in particular air quality. So gumamit pa rin ng ICP-OAS to monitor yung heavy metals natin in particulate matter 10 or PM10 in air. So sugarcane burning yung naging scenario nila. Life below water. So the last item for atomic spectroscopy is XRF. The use of XRF to analyze chemicals, in particular metals or elemental analytes in polystyrene foam in the marine environment. So life below water yung may hit natin dito. So very alarming nga, di ba, yung plastic pollution scenario natin at the moment. So it's actually a good study to perform kasi ang laki ng relevance niya globally. Kasi we really need a lot of studies pa to establish regulatory limits, regulatory policies para ma-address yung plastic pollution and the related na mga risks involved. For example, in this case, yung presence ng metals doon sa additives ng plastic. Moving on, we have the applications naman of the SDGs or of molecular spectroscopy rather to achieve the UN SDG. So medyo local tayo dito. So we have a recent research lang performed by one of our graduate residents, Jessa Luterio, who just earned her master's in chemistry degree a few months ago. So the title is Influence of Precursor Chemistry in the Property of Carbon Nanodots and its Applications for the Degradation of Methyl Orange. So in this scenario or in this study, what we used was seaweed. So extracted yung carrageenan, and then yung carrageenan was used to synthesize the carbon nanodots. And those carbon nanodots were utilized to degrade certain dyes. And in this particular setting or experiment, it's methyl orange. So ano may hit natin dito? Clean water and sanitation, life below water, and then life on land. So marami kasi methyl orange can become a pollutant to all these or can become pollutant to all these systems. Next would be another local. When you say local, the CIF based study. So it's a study by another graduate resident. So Adrian Go, the dragon. And so the title is Photocatalytic Degradation of Levofloxacin using hydroxyapatite nanorods. So hydroxyapatite here in this case was extracted naman from mussel shells or tahong. Ayan. So another rising threat is the presence of antibiotic residues in the environment. So it can lead to antibiotic resistance na hindi natin gusto kasi hindi na sila gagana sa atin pag nag-take tayo ng antibiotic. So it's there is a rise in the there's an urgent requirement siguro I guess for these types of studies, and then yun yung ina-address na tong particular study nito. So what he used here was UVVS to assess the photocatalytic activity of the hydroxyapatite on the degradation of levofloxacin. So you can perform similar studies then if you want. So medyo malaliw tayo ng konti. We have industry innovation infrastructure and SDG 11 sustainable cities and communities. Here we will be the study was focused on cellulosic fibers, and these were assessed quality assessment by FTIR spectroscopy. So you can also use FTIR for engineering and infrastructure related studies. And we have the last research here or application trying to achieve a zero hunger naman. So nasa food chemistry topic to, solubilization and extraction of curcumin using green, sustainable, and food-approved surfactant-free microemulsion. So ang ginamit naman dito ay isang dynamic light scattering system. So ayun, that's the last one. I hope you've gained some insights on how we can use atomic and molecular spectroscopy in sustainability research. Thank you so much. If you have questions, please email me at cristian.argamino@dlsu.edu.ph. Thank you for listening, and see you all later at the Q&A session.